The other example when we use lines in space, the other application problem that we did, 8th period was able to do it with me on Wednesday, and we didn't have enough time 4th period. So hopefully, and anyone that was absent, hopefully this is helpful. First thing I want to do, this is in Cartesian form, this is in parametric form, and to be perfectly honest with you, vector form is easier with both of these. So if you remember, this is like saying x minus 1 over 2 is equal to, this one has mu, let's use lambda. And so this would become like x minus, not like, this would become x minus 1 equals 2 lambda, therefore x is equal to 2 lambda plus 1. And so this, if you remember, this becomes the part of the denominator becomes part of the direction vector, and the numerator becomes part of the position vector. So for this one, we've got x, y, z is equal to our position vector plus lambda times our direction vector, so far was 2. And so then this one would become a negative 2 over a negative 1, and this one would become a 0 over a 3. Okay, this one should be a little bit easier to work with. This is x, y, z is equal to position vector plus, this is mu times our direction vector. Sorry, I ran out of space. On this one, I have 0 mu and 2 for the position vector, negative 1, and then 1 and 2. Okay, so I've got these two lines in space somewhere. And to be perfectly honest with you, they may or may not even be on the same plane. It could be, remember, so here are my two lines. Hopefully this works in the video. They could be parallel, and they could be intersecting where they're actually touching and they have a point in common. But it could be where this one is at on a different plane. You could have skew lines. Like if you notice here, those lines aren't parallel. I mean, the video makes it seem like they are, but if you think about it, you could look at, okay, off of my desk. Here's that cube that helps put the date, you know. I can look at this side right here of the cube, and then I can look at, say, this side. I don't mean side, I mean edge. Let me try and say that again. This edge right here of the cube and this edge of the cube. This video is terrible. Okay, but pick a box, and this would be parallel to some different segments, but it would be skewed to some other ones, like this one right over here. So notice that these would never, ever cross. Okay, they're not parallel, but they're not crossing. That's called skew. So for our purposes in this problem, they said find the angle between the two lines. They don't even really care if they intersect or not. If they intersect and they actually cross, fantastic, but if they don't, then what we're doing is we're pretending like we can look down on the two lines. And so you'll notice when we look at that, we have two pairs of angles, like this guy is congruent to that one, and this one is congruent to that one. So when they say find the angle between the two lines, what they'd like for you to do is to find the acute angle. Unless it's perpendicular, then just give me the right angle and you're done. So what we need in these two problems is we need to know, we don't care how to get to the line, we just need the direction of the line. And so same with this one over here. It doesn't matter where those lines are in space, we're just looking down on them, and all we're concerned about is the direction of this line and the direction of that line. And if you remember, cosine of theta is equal to A dot B over the magnitude of A times the magnitude of B. But if we want to make sure that it's the acute angle, we need, if you remember back to your unit circle, cosine is the x value. If we want to make sure it's an acute angle, we need it to be in quadrant 1. And so that means that the x value needs to be positive. It would be okay if the x value is 0, because then that would give you a 90-degree angle. So we want to make sure that it's positive, so we're going to come back to our formula and tweak it a tiny bit and take the absolute value. So notice, you got to love math. These bars represent absolute value, and these bars represent magnitude, and you do need to know the difference between them. Keep in mind, the scalar product gives you a scalar for an answer, and so taking the absolute value of a scalar is what we're doing, whereas these are vectors, and so we talk about the magnitude of the vectors. Okay, so now we are going to say, okay, cosine of theta is equal to the absolute value of the dot product of our two, here they are, direction vectors. And that's 2, negative 1, 3, dotted with 0, negative 1, 2, over the magnitude of those. This is 4 plus 1 plus 9, that's 10 plus 4 is 14, and this is 4 plus 1 is 5. Okay, so now I have cosine of theta is equal to the absolute value of 0 plus 1 plus 6. Oh, it was positive anyway. We were fine. What is that, 50, 70? Sometimes I don't even bother to multiply them, but this time you're welcome. I don't know, whatever. Okay, so we have that cosine of theta is equal to 7 over root 70. And here's where I'd need to grab my calculator. And typically we answer these questions in degrees. So you'll notice I am in degrees. So I've got 7, oh, you can't see it. I've got 7 over root 70. And now, oh, look at that. And now I want to do the inverse cosine of that answer. And so the angle here is about 33.2 if we give it 3 sig figs. So theta is about 33.2 degrees.